Hi everyone. Today we'll be talking about the Bellman-Ford algorithm, and it is a single source shortest path algorithm which can also work on negative edge graphs. So according to the algorithm, firstly we initialize all the vertices to infinity and we set the source to 0, and then we relax the edges accordingly. So after showing you the simulation, I'm certain you'll understand what I'm talking about. So let's get on with it. So all the vertices are initialized to infinity, and the source vertex is initialized to 0, and the pi array, which is the parent predecessor array, it is initialized to null. But I guess I don't need to write that because initially it will be null anyway according to the algorithm. Okay, so from the source we then go to the next vertex, the adjacent vertex, which is A and C. So we update the edges. If according to the algorithm, if dv is greater than du plus wuv, that's the algorithm, is dv is greater than du plus wuv, then we update the vertex. So we write dv equals to this plus this. If it's greater, that means we're trying to find the shortest path. So we're trying to, like, if the current value, if the current distance is greater than the added distance with this one and this one, then of course we'll update the distance only if the added distance is lesser than this one. So since it was infinity at the beginning, so we then update it to 0. S is 0 and this is 5, so 0 plus 5 is less than this one, so of course we update it to 5 since we're trying to find the shortest path. Okay, 5. Okay, so then for C as well we do the same. So we update it to -2, and then we write the predecessor as well. Don't forget to write this. It's better to keep track of what you're doing. Okay, now S is like we're done with S. Now we go select anyone, either one. You can start from A or C. We'll just go alphabetically. S is done. We just put a mark here to indicate that we're done with it. Then we go to A. From A there is just one, which is one out degree arrow which is B, which points towards B. So A is 5. 5 plus 1 is 6. So we update it to 6, and the predecessor is A. Yeah. So 5 plus 1, 6. Remember, we have to add the current value with this wuv weight, so that that is the correct way anyway. So then we go from, now that A is done, we go to B. We select B, or you could select C, like your wish. We're going serial wise. So from B we have 3 out degree arrows, C, D, and T. So B's value is 6. 6 plus 2 is 8. So we go towards C. Oh, sorry, we don't update C because from B to C the distance is 6 plus 2, 8, and 8 is greater than -2. So we shouldn't update it because we want the shortest path, remember? So -2 will still remain the same. And then from B to D we update it because infinity is of course larger than 6 plus 7, which is 6 to the 12, which is 13. And we write the predecessor, which is B. And then from S to T is infinity, we obviously update it. And then B is 6 plus 3 is 9. So 9, and then B. Okay. And then so we are done with B. Now we go towards C. We take C as the source. Now from C we go to we go from -2 plus 2 we go to A, and since A is 5, and then -2 plus 2, C from here C -2 plus 2 will give us 0. So we obviously update it because it's smaller. So the new parent is C. And then from C there is no other. Oh, there is another arrow which goes towards D. And C is -2, and D this weight is 3. So -2 plus 3 is 1. So we obviously update this one as well. So 1. And then C. So we're done with C. Now we go to D. And then from D we go towards T. And D has the new weight of D, distance of D is 1. So 1 plus 10 is 11. We don't need to update it because the current distance is smaller than 11. 9 is less than 11, so we don't need to update this one. Okay. So yeah, so this is the first iteration. From T there is nothing, no out degree arrow, so we don't need to go here. Okay, so this is the first iteration. Now for Bellman-Ford, there are like V minus 1 iteration, as in if there are V vertices, how many vertices are there? 1, 2, 3, 4, 5, 6. So if there's 6 vertices, we have 5 iterations. So we have to do this 5 more times until we get the shortest distance. Okay, so let's do it one more time. Let's start from S. S is 0. From S to A is 5. We need to update it because 0 is smaller, and S to C is minus 2. It's already there. And then we take A. From A to B is A is 0, and from 0 plus 1 is B. So 0 plus 1 is 1. So we just update this one because previously it was 6, and the predecessor is again A. Since we were writing it everything new again, so we just might as well write this as well. Okay, and then after that, from now A is over, and then we go to B. From B, the new distance is 1. So 1. So from B to C, 1 plus 2 is 3. We still don't need to update it because minus 2 is obviously lesser. And then 1 plus 7 is 8. We don't need to update it because it's 1. And 1 plus 3 is 4. So we do need to update this one. So 4, and then it's still B, but let's just write it again. And then B is over, and then we go to C, and then C, the C then value is minus 2. Minus 2 plus 2 is 0. We don't need to update it, it's the same thing. And minus 2 plus 3 is 1. We don't need to update it, it's still the same. Okay, and then D. D, the value is 1 this time. So 1 plus 10 is 11. We don't need to update it because 4 is obviously lesser than 11, smaller than 11. And then T, there's no out degree arrow, so we didn't do it. So I'm just showing you this one the last time. This is the third iteration. And then from S 0, and then S to A is 5. We don't need to update it because 0 is lesser. And then S to C is minus 2, the same as before. And then from A, the new distance is 0. So 0 plus 1 is 1, B, we don't need to update it, and then there's no more arrow. And then from B, there's 1 plus 7 for D, we don't need to update it, 1 plus 2, 3 for C, we don't need to update it, and then 1 plus 3, 4 for T, we already have it from before. And then from C, well, it seems like it's not gonna change anymore, so let me just finish with this iteration, and then I'll show you what happens if it doesn't change. Okay, so third, so from C there's it's not gonna change anymore again anyway because it's been minus 2 for a long time. Okay, and then from D, it's been 1, so 1 plus 10 is 11. We don't need to update it. And then from T also there's no out degree arrow, so no more updated anyway. So till the 5th iteration, it will still again be same since it's not changing in the 3rd iteration as well. So we can say that this is the shortest path. Okay, so that's about it for the iteration. Now for detecting the negative edge weight, what we do is we just go to this, we just go and check, we just do the iteration one more time, since like I said, if there's 6 vertices, we do 5 iterations, right? And then the 6th iteration, we go again, do the 6th iteration, and if that time also, if this still relaxes, means if the value, if the distance is still change, that means there's we can say that this like the negative edge cycle has been detected. So for this, like the negative edge, report that a negative weight cycle exists. Only if in the 6th iteration it still changes. 6th iteration as in the Vth iteration, the last vertex iteration, if it still changes, if the value of the distance still changes, if it still relaxes again and again, then we can say that the negative weight cycle exists. Now for the complexity of Bellman-Ford, See, this is order v because it's going from v, the whole loop is going up till v, and then this is order of e, this inner loop. This is obviously order of 1 because it's just one action that's doing, it's an if function. So the total analysis shows that the whole complexity of Bellman-Ford is order v into e, because this is a nested loop. So we just take order v and like this is order v plus order v into e, and since order v into e is greater than order v, we just take order v into e as the greater one. So that's the final time complexity. So yeah, that's about it about Bellman-Ford. I hope you understood. I hope you understood my explanation properly, and well, please subscribe if you want more tutorials, and thank you for watching.